So we've got two pulleys now, three boxes, and all things moving in different directions. So here's the diagram, and the first thing we're going to do, as usual, is to put the forces on the diagram. We've got the weight of box A, the weight of box B, and the weight of box C. We've got the normal reaction from the surface on box B. We've got friction. We've got the coefficient of friction is 0.7. And we have tensions in the string. I've got two strings, this one here and this one here. So I've got likely two different tensions as well. So I'm going to call those tensions T1 and T2. The pulleys are smooth, so these two tensions are the same as those two tensions. These two tensions are the same as those two tensions. So now I can resolve for particle C downwards. I'm resolving in the direction that the acceleration would take place. So that's going to accelerate in that direction. B is accelerating in that direction, and A is accelerating in that direction. So that's the directions. Those are the three directions I'm choosing for my resolving. So for C, I get 17g minus T2 equals mass times acceleration. For B, horizontally, we get T2 minus T1 minus friction is mass times acceleration. And then for A, resolving upwards, T1 minus 5g is 5 times the acceleration. So lots of unknowns apparently in these equations, but the nice thing about these three equations is that I've got a minus 2 T2 here and a plus T2 there. So if I add these two equations together, that's going to eliminate the T2. And I've got a minus T1 and a plus T1 there. So if I add these two equations, I'm going to eliminate the T1s. But actually I can do something smarter than that and save more time by adding all three together. And when I do that, I get 17g minus 5g gives me the 12g. These cancel, leaving minus fr, and then adding these together gives me 28a. So in order to find the speed, I'm going to need the acceleration here. So it's going to be helpful for me to find the friction. So I'm going to find the normal reaction here first. So resolving for particle B upwards, I get the normal reaction minus 6g equals 0 because there's no acceleration in that direction. So the reaction is 6g. And then because we've got some acceleration going on, the boxes are all moving, we know that the friction equals mu times r. We're given mu, we know what r is. So that's the friction, 4.2g. I can pop that into there and then use this equation to find the acceleration. So now we're looking at constant acceleration, we're looking at suvat. So I'm looking at the motion of particle C, box C, downwards. So S is 1.8, box C moves a total of 1.8 meters from rest, so the initial velocity is 0. I'm going to call the final velocity capital V, the acceleration we've just calculated, and the time we're not interested in. So we want the formula that doesn't include t, and that's v squared equals u squared plus 2as. Popping the numbers into that equation gives me that, from which I can find the final velocity when c hits the floor as 3.13 meters per second. So just reading the question, we've got to state modeling assumptions, and I've assumed that the strings are light and inextensible, and I've taken g to be 9.8 meters per second. So there we are.